Similar example to the seagull and shellfish, we have a ball which is thrown with an initial velocity of 8.3 meters per second up. So we're not just dropping the ball, we're tossing it up. So VI 8.3 meters per second up. Question A is asking what maximum height above its starting position will the ball reach? So what displacement will the ball have? Since the ball is in free fall, it's subject to gravity, we can use acceleration due to gravity, which is 9.8 meters per second squared down. And as we can see, we have a direction issue here. We need to have them both the same way. Since I have space with G, I'll change it to negative 9.8 meters per second squared up. And as this sits now, we still do not have enough information to answer the question. None of the formulas that we have just these three variables in them. They all have something else. But if we think about this, the ball is being thrown up, and eventually it gets to its maximum height here, and then it starts dropping down. The one thing we know at this maximum height is that just for an instant, the ball stops moving. And that means that the ball's VF would equal 0. Now you might be thinking, well, no, the ball keeps falling down and its VF gets larger towards the ground, but we're not concerned with any of this part of the ball's motion. We only care about from the time the ball was tossed until it reaches its maximum. So at that point in time, the VF would be 0. Knowing this, we can go back and pick a formula that we have used significantly. VF squared equals VI squared plus 2A delta D. Substituting in, VF is 0. VI, we actually know VI. That would be 8.3, which is squared, plus 2. A is negative 9.8. And delta D we're trying to solve for. Working this out, 0 squared is 0. 8.3 squared is 68.89. We can multiply the 2 and the negative 9.8, gives us minus 19.6 delta D. Can move the 68.89 over. Gives us negative 68.89 equals negative 19.6 delta D. Divide both sides by negative 19.6, rounding this to 2 sig figs, means that the ball gets to 3.5 meters above its initial height. Question B, at what time interval will the ball return to its initial position? Well, I'm just going to clear the page for this just for a second. So we have the ball, it's here. It's tossed up, hits its peak, and it comes down, and we want to know how much time has gone by between being thrown up and passing by its initial position on the way down. The issue with this is that we can't deal with the whole motion, but we can deal with half of the motion. We can deal with the time that the ball is thrown until it hits its peak. We've dealt with that for the maximum height of the ball. We know VI is 8.3, VF is 0, and the other thing we know is that this will be symmetrical. So however long it takes the ball to leave the hand and get to the peak is the same amount of time as it takes the ball to go from the peak back down to its initial position. So now that we're trying to solve for the time, same variables come into play, VI, VF, A. Easiest equation to use would be VF equal VI plus A delta T. VF is 0, and again, this is just to the peak of the ball's flight, not the whole motion. We'll compensate for that later. VI 8.3, A was negative 9.8. Can move the 8.3 over. Divide by negative 9.8, round it to 2 sig figs. We get 0.85 seconds. Specifically 0.85 seconds to the peak. This is half of the motion we're looking at, so to get the full time to get back down to the initial position, multiply this by 2. So the entire time to get from ball released up to the peak and back down would be 1.7 seconds.